These are the exercises that we're going to solve in this video, so if you want to try them first, just pause now and solve them and then come back. A lot of times people get confused by the use of the word locus. This is not anything difficult, it is just a word, and it means you're going to find an equation, okay? I know you are starting from an equation already. By the way, I'm going to do letter C of the question. But that is a complex numbers equation. You're going to find a Cartesian equation instead. That's going to be the locus. So basically what this is turning one type of equation into another type of equation. It's supposed to be an algebraic manipulation exercise. But the reason why we have a word for it, for the locus, is that solutions to complex numbers equations are able to do a lot more than solutions to real numbers equations. Because if you think about it, you have a equation in real numbers, you're going to have one solution or two solutions. You're going to have maybe a bunch of solutions, but they are just a set of points. They are not very interesting. It's very difficult even to find intervals as solutions to equations in real numbers. You find intervals as solutions to inequalities, but not to equations like this is. Now, in the complex plane, this becomes easier to do because you don't necessarily need just a bunch of random scattered points. Sometimes your solutions will be interesting shapes. They will be curves. And that is what the word locus means. It means that the set of solutions to an equation has an interesting shape. Because it's interesting, it gets a name. Anyway, we do part B, for example. The argument of z minus I is pi over 6. So you have the I here. Your z will be something, for example, here, such that z minus I, which is this, has an argument of pi over 6. But nobody said anything about how far away from iz is. It's just that it has this argument. Nobody said anything about the modulus. So any z along this line will do, which means that the locus is the equation of this line, which is this one. You just think about the slope of the line, the rise over run, that's the tangent of pi over 6. So that's the answer to part B. You might as well try to do part A as well. The conjugate is equal to minus iz. So here's z, here's the conjugate. Iz is a 90 degrees rotation that way, and minus Iz puts me on the other side right here. So these 2 points were supposed to be the same, right? The conjugate and the minus Iz were supposed to be the same. That's going to happen when theta is 45 degrees. So y equals x is the line with 45 degrees, slope 1. That's the solution to part A. Part C, however, is a lot more interesting than both of these, because what does he want? He wants the distance between z and 3 and the distance between z and minus 3 added together to be equal to 8. What does that sound like? The sum of the distance to a point and the distance to another point has a constant value of 8. That locus is an ellipse. Well, maybe you're not used to thinking about the absolute value as a distance, and you wouldn't have read that equation the same way that I did. But this is also very useful to know. The first time you ever learn about absolute value is way before you learn about complex numbers, so you don't think of it in terms of an Argand diagram. Somebody in your life probably told you at one point that the absolute value is the number without the sign, which works fine for the real numbers, right? If I want the absolute value of x to be equal to 3, the solutions to that equation are 3 and minus 3. But things get a lot more interesting when you move from the real numbers to the complex numbers. So you should never ever read this as the number without the sign. You should read the absolute value of x as the distance from x to the origin. Because when you put that in the complex plane, now there is a whole circle of numbers. It's not just 3 and negative 3. Anybody in this circle has an absolute value of 3. With different arguments, of course, but that's not what distance cares about. And then if you just do a horizontal translation 5 units to the right, for example, what are the numbers that are going to be 3 units away from 5? Well, that's 8 and 2. So that's why this should be read as the distance between x and 5. So this is the distance between z and 3. This one is the distance between z and negative 3. So this means that the sum of both of these distances is constant, equal to 8, and we know that that makes an ellipse. We even know that the center of the ellipse is at the origin because of the symmetry of the 3 and the minus 3. So we just need to figure out the values of a and b. This is going to be the value of a, that's going to be the value of b. So a is the following. A minus 3 is the distance between this point and this point, and those two things added together need to be 8. So that means that a is 4. Now let's try to find b. This one plus this one is the whole 8. It's the length of the string. So each one of them is 4 because that is symmetry. This is 3. Pythagoras is going to give us the other one. B is the square root of 7, which means that b squared is 7. And that is the locus of the thing that the question was asking for. Now, if you want to see how useful it was to have this information about ellipses, just try to do this one exercise without using that. What you're going to do is you're going to replace the z by x plus iy. You're going to do the same thing here. And then it's going to be a whole lot of algebraic madness until, if you don't make any mistakes, you will get to the same conclusion. But I got there without calculating almost anything because I knew this shortcut. So I was saying that this exercise uses the word locus because the set of solutions to the equation is going to be an interesting shape, right? A curve. It doesn't just have to be a few scattered points on the plane. And I said that this happens because the complex numbers have a lot more space, the solutions have a lot more freedom of where to move, but this doesn't always happen, like for every equation in complex numbers. This doesn't necessarily happen. You will see that these equations in exercise 17 where this is happening, they are involving some very specific things about complex numbers. Like this one uses a conjugate, this one talks about the argument, this one involves the absolute value in the equation. But when you move to the next exercise, which is also just solving equations for complex numbers, they don't have that. It's just the complex number to the power of a number equals another number. And the next one is exactly the same kind of equation. It's z to the power of 3 equals a number. I know that this one looks a little bit more complicated than the previous one, but it's just because of where that number is in the plane. Like minus 8i is here, and 2 plus 2i is somewhere over here. So it needs to be expressed with a plus, which makes it look like the equation has one more element than the previous equation, but it doesn't really. It's just z to the power of 3 equals a number. So for this type of equation, the set of solutions is actually just going to be a few points on the plane. In fact, these are all polynomial equations. So z to the power of 3 equals a number. You expect there to be exactly 3 solutions, so 3 points. It's not going to be a curve. And this one, z to the power of 5, you're looking to find 5 points. And you're going to solve all of these equations in the exact same way. It's a step-by-step process because it is the same equation over and over again. It's z to the power of a number equals a number. So let's start with 2a, and the thing that you do first is that you can find the most obvious of the points that you can think of. You know that you're expecting to find 3 solutions, but let's find one of them first. And we're going to do that by thinking first about the modulus and then the argument of this solution. Minus 8i, like I said before, is down here. So when you take your solution and put it to the power of 3, the modulus is 8, and the argument is all of this. So z should have a modulus of 2, because 2 to the power of 3 is 8. Imagine that this is a circle of radius 2. It's not that the whole circle is solutions, but the solution that we're talking about is going to be somewhere on that circle. In fact, all 3 solutions are going to be there because the modulus of the z needs to be 2. So we're looking for 3 points on this circle. And what does the argument need to do? Well, when you take your z and put it to the power of 3, you're going to use the argument of z 3 times. So it's going to go 1, 2, 3, and reach the argument in the bottom that we had mentioned before for the pink point, which means that the argument of z needs to be a third of that. So 2i is our first solution. When you take the number 2i and you put that to the power of 3, you get negative 8i. So that's the first part of the process, is figuring out one of the solutions. Now let's look for the other two, because we want there to be three in this case. And if you are following the playlist of complex numbers, the next video on this playlist, I'm going to go into more detail about this. But the thing is that we know for a fact that the other two solutions are also on this circle of radius 2. And the other thing that we need to keep in mind is that the three solutions are equally spaced around the circle. So it's not like you can have that one and then this one and this one. This doesn't work. You have to have three equally spaced points along the same circle, which means that you have to take the full angle of 2 pi and divide that by 3. So 2 pi over 3 is going to be the angle between the solutions. We already have one up there, so we need to have one here and one here. So the angle of 2 pi over 3 is this angle here, okay? It's not the argument of the second point. The argument of the second point is going to be this pi over 2 plus this 2 pi over 3. That's 7 pi over 6. So we can write the name of this point here. He is 2 e to the power of I 7 pi over 6. And then you can do the same thing for the other point. In this case, the 2 pi over 3 is here, which means that his argument, which is just this little thing here, is minus pi over 6. You could have also done this going the other way around, okay? Like all of this way, and then it would be 11 pi over 6. Sometimes this is going to depend on the question. Some questions specify a domain where they want the arguments, but this one didn't. Anyway, I'm not going to do part B because it's just the exact same thing, only with 27 instead of 8. So you're going to get the same shape. A picture is going to look exactly the same, but instead of 2, it's going to be 3. Let's do 6a instead. That's more interesting because instead of this point down here, we are going to have 2 plus 2i. So 2 plus 2i is that point. It is right in the middle of the first quadrant. It has an argument of pi over 4, and the radius is 2 root 2. And this is also a z to the power of 3 that we're looking for. So for the modulus of the solutions, we want the square root of 2, because when you take the square root of 2 and put that to the power of 3, what you get is 2 root 2. We're looking for solutions along this circle. This is the circle of radius equals the square root of 2. Now let's figure out the argument for one of the points first, and then we're going to put the other points. So when we put our z, the solution to the equation, when we put that to the power of 3, the argument needs to become the pi over 4 of this number. So it needs to be a third of that. It's going to be pi over 12. In the picture here, I'm trying to split that slice into 3 equal looking parts. But anyway, this blue point here is already one of the solutions, which is root 2 e to the power of I pi over 12. What are we going to do about the other ones now? Well, they have to be equally spaced along the circle. So they need to have 2 pi over 3 of angle between them. But on the previous exercise, the first solution was aligned with one of the axes, so it was easier to calculate. In this case, it's not. Our reference is this blue point, which is at a weird angle of pi over 12. But we still try to draw it in the same way, and the only difference is that now I can't do the calculation in my head. I have to write it down. So what is pi over 12 plus 2 pi over 3? 9 pi over 12, which happens to be 3 pi over 4. That's a good-looking answer. It even makes me want to convert this number back into Cartesian form because it looks so simple. It's just minus 1 plus I. But for the other one, I'm probably not going to do that because it's going to be pi over 12 minus 2 pi over 3 this time because I am moving in the opposite direction in the circle. That's negative 7 pi over 12, which is just a strange looking number. So let's write down our third solution to the equation is exactly this. So as expected, we found 1, 2, 3 solutions. They are just 3 points in the coordinate plane. I am not going to solve the other items in this question because they are all the same, but you should definitely do this for practice. One little thing that is worth mentioning here is that in a previous video of the playlist, we were talking about polynomial equations. And one of the things that we go through over there is that complex solutions to polynomial equations always appear in conjugate pairs. That was one of the rules we were talking about in that video. But if you look at what's happening here, this is not happening. These are polynomial equations. It's z to the power of 3 equals 2 plus 2y. And it does have 3 solutions because the degree of the polynomial is 3. It does have complex solutions, but the complex solutions are not appearing in conjugate pairs. You have a complex number as a solution, and its conjugate is not also a solution of the same equation. But the thing that's happening here that I don't want you to get mixed up in your head is that that rule about the conjugate pairs, that only applies to polynomial equations with real coefficients, okay? So these equations that we are working with today, when he says z to the power of 3 is equal to 2 plus 2y, 2 plus 2y is not a real coefficient. It's still a coefficient that is appearing in the polynomial. It is the coefficient of the term of degree 0, but it's not a real number. So that takes us away from that situation in which we knew that the rule was that complex solutions always appear in conjugate pairs. And as for the last exercise on our list, number 13, now we are back to working with absolute values in the equations, just like we were in the first exercise. So again, I am expecting to find a locus of solutions. However, the question is phrased in a slightly different way. He doesn't use the word locus this time, because notice what he is doing. He is being sneaky this time. He says, find the absolute value of z. He's not actually saying solve the equation, which is find the values of z. Find all the possible points z, which would in case be a locus, because it is going to be an interesting curve. No, instead he just says to find the absolute value of z. And what this implies is that the locus is a circle, but it's not any circle. It's a circle centered on the origin. Well, actually, he's not saying that much. When he says find the absolute value of z, he is not really implying that every z that has that same absolute value would be a solution. What he's actually implying is that all solutions that exist will have the same absolute value, so that the question makes sense in the way that it is phrased. But it does turn out as to be a circle, as we will see. So we've talked about this before. The absolute value of z plus 4 is the distance between z and the number -4, which I'm going to put here. And the absolute value of z plus 16 is the distance between z and -16, which I'm going to put here. So we are looking for a point. Here's the thing, we know that there can be many solutions, but we also know that it's implied that all of them have the same absolute value. So it's enough for us to find one of them as a student who is solving the question. We don't need to consider finding all of the solutions, or does the whole circle consist of solutions? Is it a locus? We don't need to think about that. We just need to find one solution and say its absolute value. So we're looking for a point that has this relationship between the distances to -16 and -4, right? He is twice as far from -16 as he is to -4. And then we just drew a picture. So we look at the picture, and this is the point. The point is -8. This distance is 4, so 2 times 4 is 8, and this distance is 8. The exercise itself is finished. All that you have to do now is draw a similar picture for part B and figure out what the answer is going to be in that case. But there's a lot more interesting stuff that we can do here just to see what we can learn. Let's keep in mind the idea that knowing certain things is sometimes helpful. So let's see what we can learn from this situation, because we think there might be a whole circle as a locus of solutions to this equation. So I think the easiest thing that we can do first is to check if the other 8s on the axis also solve the equation. This one clearly does, because this distance is 12 and the other one is 24. This other one is not so clear, but if you have patience and you do a Pythagoras here and another Pythagoras here, you will see that it does work. This one's going to turn out to be this number, which I don't care to simplify right now. It's 4 squared plus 8 squared, and then the square root of that. And calculate the other one if you want. It's going to turn out to be twice of that. But the thing that takes a little algebraic work is to figure out if every point on the circle that we are thinking is actually going to be one of the solutions. Well, the only way that I can see to actually prove that is to just take a deep breath and do the calculations, which I am going to do. But before that, I want to just check that it at least looks that way. So I've typed the equation here in sort of a general way that I can change the 2 points that I'm looking at, A and B, and also I can change a value of C, which is that number that is multiplying here, right? This one is 2, this one is 3, so I have the freedom to change that in my picture as well. And notice that it's starting with C equals 1, which is just saying that the distance to this point is equal to the distance to that point, and the picture is a line. Well, that is the perpendicular bisector, the set of points that have the same distance to two given points. So that is the interesting connection here. What are we actually looking at? It is a sort of generalization of the perpendicular bisector. It's not exactly going to be a bisector anymore. This one, for example, is cutting that distance into 3 parts, right? So there's 1 here and 2 here. But yeah, let's see what happens when we change the value of C. Look, it's a circle. Or it can be a circle on the other side if the number is small, which is just flipping the equation backwards. Yeah, and when C is exactly 1, it becomes the perpendicular bisector. I can't find it exactly anymore, but it's somewhere in there. So this is always a circle, at least experimentally, this is what it's looking like. It's not always a circle centered at the origin, which in the question it has to be because of the way that he gets to ask just find the absolute value of Z. But I think that as we're doing the calculations, we are going to figure out how this happened in the question, that the center of the circle was in the origin. So let's do it. I'm just going to expand this one algebraically. All of the 18 goes with the x. It doesn't go with the y because z that we are looking for is a point x, y, and 18 is a point here. 18 is the point 18, 0. So when you do Pythagoras to calculate this distance, you get just y on the vertical and x minus 18 on the horizontal. Same thing on the other side, and I'm going to expand that. And here we can already see how that circle is going to be centered at the origin because this 36x is canceling out with this one. He chose the numbers 18, 3, and 2 very specifically so that this would happen. But as we've already seen, when we get more freedom in the numbers, like it doesn't always happen. The center is not necessarily at the origin. So yeah, this one is the letter B of the exercise done totally algebraically without drawing any pictures, which I'm sure you know I find boring. This is not a thing that I like to do. If he had not chosen the number specifically, then the 36 and the 36 would not have completely canceled. We would have something with x here, and then we could complete a square to find a circle with a different center. So yeah, that's just one more tiny little thing that now you know. Maybe it will come in handy in some question when you least expect it, right? When you see a distance equals to another distance, that's a perpendicular bisector. But when you see a distance equals a number times another distance, then that is a circle.